depending upon what this receptor is linked to. Right? If it's linked to an ion channel, you're going to get ion flux. If it's linked to GPCR, you're going to trigger or mediate a response that's a second messenger response, depending upon the scenario. Right? And you'll notice that for many of these neurotransmitters that we have on here, there are multiple kinds of receptors that will bind it. And that should make sense, right? Because if you only had one type of receptor that could bind to a particular neurotransmitter, you will only ever get one kind of response. But acetylcholine can have two different kinds of receptors. So by the way, let's do it like this. Anything that pertains to acetylcholine will use the category cholinergic, right? Anything that would pertain to epinephrine and norepinephrine we call adrenergic, because adrenaline, right? Anything that would pertain to dopamine we call dopaminergic, right? So it's just a way of kind of categorizing it. So a cholinergic neuron releases acetylcholine. A cholinergic receptor binds acetylcholine. Does that kind of make sense? And as far as cholinergic receptors, just to give you a for example, right, there are two different kinds. There's nicotinic and there's muscarinic. Okay. Now, these actually give opposite responses. Nicotinic are mostly excitatory, muscarinic are mostly inhibitory. So here, the same neurotransmitter, acetylcholine, could cause depolarization on the one hand and hyperpolarization on the other hand. Which one it causes depends on the type of receptors we have. A nicotinic receptor here is ionotropic. And what it is linked to, let me tell you what it's linked to. It's an ionotropic receptor, which is going to cause ion flux. It is linked to a monovalent cation channel. Now what did I just say? What's monovalent mean? Single charge, mono, one single charge. Cation, positive. So what is it permeable to? Sodium and potassium. Not calcium. Why not calcium? It's divalent, right? It's +2. It's too big. So if this channel is open, tell me about ion flux. Sodium influx, potassium efflux. Yeah. Do they move at the same rate? No. And do you know which one moves faster? This has nothing to do with the channel, how fast the channel opens and closes. Not that story. Sodium moves faster. Do you know why?
It's smaller. Oh no.
Is it smaller? I don't think it's smaller, actually. Or it is smaller. It is smaller, but that's not why. Because it diffuses? Yes? No. Higher concentration gradient for sodium. Remember the sodium? You were going to say that? Why didn't you say it? Why does sodium have a steeper concentration gradient than potassium? Guess what? Every time the sodium-potassium pump works, it pumps out 3 sodiums out and 2 potassium in. So which one is there? There's more sodium outside than there is potassium inside. You okay with that? So if it's open, sodium influx, potassium efflux, we would say it this way: net depolarization, right? Yeah? You like that word? Well, you have to say net because sodium causes depolarization, potassium causes hyperpolarization. But if you get more depolarization than hyper, you're going to have a net depolarization. So would you call this excitatory or inhibitory? Excitatory, because you could reach threshold as a result of that, right? Okay. Muscarinic actually are metabotropic. There, and so it works by a second messenger system. Here it's a GPCR coupled kind of thing, but what it triggers actually is it triggers hyperpolarization for the most part. for reasons that we'll talk about at a later date. And as a result, it's mostly what? Inhibitory. It's mostly inhibitory. So these are antagonistic receptors, right? But the same neurotransmitter could trigger depolarization on the one hand and hyperpolarization on the other hand. Do you know why you call a nicotinic receptor a nicotinic receptor? What else do you think it would bind? Nicotine. Assuming you don't smoke, do you have nicotine in your body? You shouldn't. Right? You shouldn't.